Let's compare a few motors that we use in the appliance industry. Here we have our PSC motor, or permanent split capacitor motor, and on the bottom we have a little cooling fan for it. That's its sole purpose right there. And up top on the motor we have our pulley. That is where the belt from your washing machine would wrap around. The motor drives it, turning your gear case or transmission. The motor itself has very nice bearings, and it should basically turn effortlessly by hand. If you do encounter one of these motors and it does not turn freely by hand, that would indicate that the bearings on the inside are starting to fail and the motor should get replaced. This motor is found in GE and Whirlpool top-load washing machines. By looking at this connector here, we can see that it uses 4 wires, and these 4 wires represent ground, neutral, and both of our hot wires for our clockwise and counterclockwise windings. If you were to ohm out this motor between neutral and counterclockwise, it should give you a resistance between 3.5 and 7, and the same thing for the clockwise winding. If you place your meter leads on both of the windings terminals, it'll place them in series and roughly double the resistance value like you see here at about 8 ohms. At no point should you have any resistance between ground and the other terminals. This right here is your classic split phase motor and is pretty much the motor you're going to find in any modern day production dryer. Similar to the PSC motor, it should turn freely by hand, but will have slightly more resistance. If we turn the motor on its side, we see that it has a larger set of contacts than the PSC motor did. If we face the motor towards the camera, it might be a little bit hard to see, but the contacts on the motor are 1, 2, 3, 4, 5, and 6. The 2 largest contacts on the outside represent 1 and 2, and that's for the heat circuit, basically completing L2 in the dryer. On the inside, there's 3, 4, 5, 4 representing the hot, and 3 and 5 representing the neutral for the start and run winding. With the motor at rest, like we see here, your meter should show open line between contacts 1 and 2. For contacts 3, 4, and 5, all that really matters is contact 4 and 5, which should have a resistance value between 1.5 and 3 ohms. This is because the start and run windings are in parallel, and they must ohm out less than their individual resistance. If we turn the motor to its side again, you see a little brown disc that slides up and down. This is our centrifugal switch. Just below it are 2 little weights that basically, when spun, or when the motor is turned on, they fling out and they pull down on the disc and engage or disengage the switches that we were just ohming out. This is responsible for disengaging the start winding and allowing the heat to come on. And here we have our 3-phase motor, which is often considered to be the creme de la creme of electrical motors in the appliance world. The motor consists of 2 different parts, the rotor up top and the stator down below, the stator having 3 separate windings. Each one of those windings has a terminal on the plug that we can see right there. The resistance across any 2 of these terminals should be the same, so if we begin to the left, roughly we should have between 8 to 10 ohms. If we go to the 2 on the right, again we have 8 to 10 ohms. And if we go to the 2 terminals on the outside, again we have 8 to 10 ohms. Another unique feature about this motor, aside from having 3 separate windings, is the fact that it requires an MCU, or motor control unit, to drive the motor. Now remember, what you're looking at is the stator, meaning it stays put, it does not move, and it bolts against the machine using those holes or eyelets right there. Here we have the rotor, and unlike the stator that rarely fails, the more common failure by far between the 2 components is the rotor itself. And if we turn this to the left, you can see that we have magnets that are visibly cracked, and this is not entirely uncommon to see. However, the magnets don't usually crack for no reason. The main culprit tends to be the inner portion of the rotor where we have our splines. Turning the rotor to the side so we can get a better look at the splines, it may be hard to see, but in this particular one, they are in fact stripped out. And the reason for this is that those splines are commonly plastic. However, the drive shaft that they link to for the basket is made out of steel, and steel wins that battle every time. So which motor is best? Going back to the split-phase motor that we find in our dryers, it's tried, true, reliable, provides tons of starting torque while we use it in the dryer, but unfortunately, it's not exactly the most efficient. Another perk to the split-phase motor would be that it is massively produced, and it's usually relatively inexpensive to replace. Going back to our PSC motor, or permanent split capacitor motor, just like the split-phase motor, it's massively produced and relatively affordable to replace. While the motor itself doesn't produce a whole lot of starting torque, it does offer a decent amount of torque when it's up in RPMs, which makes it suitable for most top-load washing machines in current production. Another nice thing about the PSC motor is that it doesn't require an MCU or motor control unit to run. It simply allows power to go from the counterclockwise or clockwise or forward and reverse windings to do its job. Another downfall is that it does require a capacitor to run, however, the capacitor is more likely to fail, making repair typically affordable. In fact, most of these motors come with extended warranties because the manufacturer knows the capacitor is more likely to fail than the motor ever is. And that brings us back to our three-phase motor. Again, because it has 1, 2, 3 windings. Now, as far as reliability goes, this is the best motor you can get. In fact, I don't think I've ever replaced one of these in the field because it's actually failed. The only time I've seen them fail is right from the manufacturer where they were faulty, or maybe some type of situation where we had catastrophic failure on the rotor. Another benefit to this motor would be that it offers tons of torque at low RPM and tons of torque at high RPM. This makes the motor ideal for higher end washing machines, especially with the front loaders. The only con that I can honestly think of with this motor is that if by chance it does fail, it's very expensive to replace.